All right, hey guys, today we are looking at our notes for air pressure. So air pressure. Air pressure is the measure of the force with which air molecules push on a surface. Don't know why that period is underlined, but again, it's the pressure exerted by air. So we know that pressure is force divided by the volume, divided by the surface area of which it's being applied at. So in this case, it's just the pressure that's applied by air. We know air has little molecules that we don't see that are bouncing all over the place. So the faster those molecules are moving, the harder they're going to bounce off of those surfaces and the more pressure that's going to be applied. Air pressure is the greatest at the surface of the Earth because there's more atmosphere above you pushing down on you. And we know that, again, the force that's being exerted here are the molecules bumping into each other and pressing down on those surfaces. So the further down you are, the harder gravity is pulling on those air molecules to provide that that force, as well as the weight. Gravity keeps pulling on those molecules, and there's more molecules of air at the surface of Earth versus way up in the atmosphere. As you move up in the atmosphere, obviously if it's high pressure towards the surface of Earth at sea level, as you go further up, there are fewer molecules to bump into you, so therefore there are fewer things to exert a force on you, therefore there is less air pressure. So the air pressure is decreasing as you increase your altitude. Air pressure in this case depends on density. So the density of the air is what is the biggest determining factor in the pressure of that air. Because again, a more dense air will have a higher air pressure because there are more air molecules that in a given space that have a chance to push down on you, bump into each other, and provide that pressure to go off of. Less dense air will therefore have lower pressure because, as you can see in the two little pictures I have here, more dense, there's more particles that are going to push against you. Again, if each of these have their own individual little force that they're applying and bumping into you with, the more particles there are, the more they can bump into you, the more force they can apply to you, therefore the greater the pressure in the same area. Where if you have a less dense air like helium, it's going to exert less pressure because it's, there's fewer molecules to bump into you with to provide that pressure. Density is the biggest thing that impacts pressure. When we're talking about atmospheric pressure, air pressure, here on Earth's surface, the three big factors that determine that atmospheric pressure, that air pressure, is the elevation or the altitude, so where it is relative to sea level, so the Earth's surface, the temperature of that air, and then the water content as well. So all three of those things will determine what the air pressure is, or have they're a factor in what that atmospheric pressure is. The elevation, again, we've already talked about this. As you move up in the atmosphere, the air pressure is going to decrease. The air gets thinner. There's fewer molecules, so therefore the air pressure is going to decrease. Like I just said, there are fewer air molecules as you push down on you in order to apply that force. So the force is going to be less, which means the pressure is going to be less. So here, just a little example, we can see we've got three different stations that we're measuring both temperature and the pressure. So this is millibars. There's a lot of different ways to measure pressure, as we've talked about. Atmospheres is another standard here. ATM, atmospheres, is literally the standard pressure at sea level. So if we're here at sea level, 1,008 millibars is what we have for our standard pressure at sea level for a given temperature. So station B, we can see it's got a higher elevation. It's 1,000 feet up. It's got 915 millibars. And then all the way up at 1,800 feet, it's got 840 millibars. So you can see that pressure is going down as you move to the right. Another thing that impacts the air pressure is the water content, which in weather terms is the humidity. That has a big impact on it, because we know that moist air is less dense than dry air, and therefore it is a lower air pressure. So water molecule has less mass than the molecules that make up that air. If you replace some of those molecules with water molecules, the water's lower density the water lowers the density of that air, and then therefore lowers the air pressure. It seems counterintuitive. It does seem a little bit backwards because, H2O, those are bigger molecules. Like you would think that those are bigger molecules, so they're more dense. So then they would increase the atmospheric pressure, the air pressure of it. But actually, it has the opposite effect because those water molecules are kind of almost acting like not only are they decreasing the density of it by taking up space that the air molecules can't then occupy. So it's a lot more limited for how many air molecules can be packed in that same area, but it also kind of acts like a buffer because those air molecules can bump into the water molecules, the water vapor, instead of the different things that it might be exerting on. So like the pressure that you might experience on your hand or in your skin or of the airplane or whatever we're talking about is actually decreased because of that as well. And then temperature, for this one, I think this one is more intuitive. The warm air is less dense than cold air. We've talked about this. When we heat up a gas, it expands those same molecules, right? They increase in size. The volume of the gas increases. So warm air is less dense than cold air. So then warm air has a lower air pressure than cold air. Again, there's the small. There might be a small confusion that you think, oh well, maybe warm air because it's warmer, it has a higher kinetic energy, so they're moving faster. But because they move faster, it is more spread out over a whole given area. Maybe the individual molecules might have a greater force that they exert, but that air as a whole actually decreases in its pressure because it's expanding, so then therefore it takes up a whole lot more surface area for that same amount of molecules. But again, like I was saying, because they're moving faster, they spread further apart, therefore there are fewer of those molecules to push on a given surface. So so a barometer, this is one of our tools to measure air pressure. There's a lot of different types of them. There's an aneroid barometer, which is there's actually a little thing that expands in here, so you can see there's a little coil. And we'll actually look at this with expansion rates of metals. When you have a greater pressure exerted on it, it actually kind of unwinds itself, and there's a little diaphragm in there that expands or contracts because of it, and that pushes on the dial to turn it. A mercury barometer. Don't know why I struggled so much with that word. Mercury barometer. This is, if you remember from the Mythbusters episode that we watched, Adam did all of his measurements when he was measuring the pressure, the negative pressure of the little cans or the containers, the tanks, the actual train car and stuff. He measured in inches of mercury. This is where that measurement comes from. It's literally when air pressure pushes down on this little pool. I think I have another picture. Yeah, here we go. So when air pressure pushes down on that pool of mercury, which mercury is liquid metal, so it's a metal that's liquid at room temperature. So it pushes down with that atmospheric pressure and actually forces this mercury up the tube, because up here in this little end of the tube is a vacuum, so there's it's just empty space in there. So it's free to just kind of move up and down without having to worry about any kind of extra pressure that's added to it. So any atmospheric pressure that's pushing down on the mercury pushes the mercury up the tube, and they literally measure it in inches of how far up that tube it's gone. So inches of mercury is where this mercury barometer is where that unit comes from. Okay, how air pressure affects the weather. So we know that air pressure in a weather system reflects the amount of water in the air, which affects the weather. So when I've actually taken a meteorology class, it was one of my grad school classes that I took. It was very interesting and very, very complex. There's a lot of different moving parts to this, but what it boils down to is in basic, as basic as we could get, a low pressure system usually results in bad weather. So when we're dealing with a low pressure, because that low pressure, the way that our atmosphere and any kind of system, a low pressure invites stuff to kind of flow in to occupy that space. If we have a low pressure, like energy, like heat, our molecules and just kind of the air itself wants to flow from a place of higher to a place of lower. So like higher heat always wants to flow to lower heat until it equalizes into an equilibrium. Kind of the same thing for electricity. It flows from a negative charge to a positive charge or vice versa. When we're talking about atmospheric pressure, our atmosphere wants to flow and try and equalize. So if we have this pocket of low pressure, due to either a change in the water content or whatever it is, a low pressure system, because all of this other stuff wants to like flow and collapse in on this low pressure area, it kind of invites all of this bad stuff to come and flow into that low pressure area. So when you have a low pressure area, that's where it starts to get cloudy, or if the other factors are correct, where you can get some storms, you can get some rain, that's always because stuff is all flowing and collecting together, and that kind of just dumps on this low pressure area. Where if you have an area of high pressure, so if you have high atmospheric pressure, because again, the area wants to equalize and try and be at equilibrium for the air, that atmospheric pressure, if you have a system of high pressure, it kind of pushes all the bad stuff away, and that's when you have clear sunny days and you have this nice weather. You might have some breeze, because if you have a high pressure, it wants to flow to a lower pressure, and that's actually where wind comes from. So that's kind of as simple as I can make it. Low pressure, bad stuff. High pressure, good stuff. And that's actually something you can look at, because if you look at like the little high pressure bands or low pressure bands, the little areas of H's and L's as well, warm fronts and cold fronts and all this other stuff, that's all caused by just changes in pressure, changes in water content and all that good stuff. You can see in these, anywhere you have that low pressure system, that rain, that warm front and that cold front might interact with each other in a low pressure area and dump all of the water there, because in a low pressure area it's all going to flow there. If it's got a low pressure area that hasn't equalized yet, it's going to sit there for a little while, and it's going to continue raining and continue dropping all of that water that it's gotten built up in its clouds. And that's kind of where that comes from, where if you look at these high pressure areas, everything is kind of being pushed away from it. That warm front is being pushed away from it, and you can see it's just dry. Maybe it's a little chilly, maybe it's a little windy, but you can see that middle of America here right above Colorado and Wyoming and stuff, and you can see there's not a whole lot going on there because it's a high pressure area. Everything else is just kind of flowing away from it. So something you can look at to actually understand what some of those maps are that meteorologists show you. That's all we got for today. So if you have any questions, concerns, thoughts, ideas, hopes, dreams, as always, make sure you guys are reaching out and letting me know. Otherwise, have a fantastic day. We'll see you soon.